we'll do a derivation. Then we'll do a simulation. And then the simulation will also have an animation, so you can visualize what exactly goes on. And just by looking at it, you may be able to say, okay, this looks meaningful or doesn't look meaningful. Okay, so first let us model the system. So that's link 1, and then we have a link 2. I'm just going to assume they have equal lengths. Okay, let's place the center of mass somewhere on the pendulum, the links. And let's say that this is at a distance C1 from the top pin joint and C2 from the second pin joint. Okay, and both these are going to be of length L, which, by the way, is just simplify the equations, but it doesn't have to be. Symbolic toolbox will take care of this even if you have different lengths. Okay, let's call these some of these points. It will help us in derivation. G1, G2, and this is, let's say, O, and then this point, which is the second joint, P. Okay, so let's say that this is mass M1, inertia I1, M2, I2. Okay, now inertia is usually 3 by 3 matrix. So there are 6 unique numbers which describe the inertia of a 3-dimensional body. But when you look at 2D, what matters only one inertia term, which is basically the inertia about the axis, which is pointing outside the plane of the paper, right? The z-axis. So it's just a single number. We'll talk about 3 dimensions a bit later. Okay, and the last thing I need to derive the equations is set up the axis. So I set up the frames. So first, my world frame is going to be x0, y0. So that does not move, it's fixed. Okay, now I'll specify axis for each of those links. So 2 links to axis. Okay, x2, y2, x1, y1 for each of the links. And then I need to specify the degrees of freedom, which I've not done so far. So this angle is θ1, and θ2 is the angle made by the second link with the first link as shown here. Okay, so we'll follow those 3 steps. And once you do the 3 steps, you'll get the equations of motion. And then the last step is to use a numerical method to integrate the equations. I'll use the ODE int, I think, to integrate the equations. So step number 1. So let's compute the position of the center of mass. Now you always want it in frame x0, y0. Okay, that's a fixed frame. So what I'm looking for here is G, or let me use capital G since I use capital G in my paper. G1 in frame 0. So Now, if you go back to look at homogeneous transformation, you know that G10 is basically related to the position of G1 in frame 1, so X1, Y1, by this transformation matrix H. So as long as I have those two things on the right side, I can compute G10. So H10 is R10, O10, 0, and 1. Okay. Where R is the rotation matrix associated with θ1, and then O10 is the location of the origin 1 in frame 0. So here it happens that this is O00, but it's also O10. Okay, so let's write those things down. Now, we know that the rotation matrix is 2 by 2. It's like cosine theta, sine theta, minus sine theta, sine theta, cosine theta, right? Now, in this case, in the derivation, if you remember long time back, the angles are always defined with respect to the frame, to the x0 axis. So here, if you see, this θ1 is not quite about the x0 axis. It is about the negative y0 axis. So I need to find the angle with respect to x0 axis. So you see this. This is x0. The pendulum is like this. This is θ1. So I need to find the angle from here. And so you should always be the angle with the positive x-axis. So if you want to compute that angle, you need to go all the way here to this. And so that angle is, well, it's 90 plus 90 plus 90 plus θ1. So it's 3 times 90 is 270. And so that's the angle which will go in the R. So that formula which I had for R needs that angle. Okay, now there are other ways to do it, which is you can define a clockwise angle and do it that way too. I just think it's just better to stick to the convention which you used. So this rotation matrix is cosine 270 degrees plus θ1 minus sine 270 plus θ1, sine of 270 plus θ1, cosine of 270 plus θ1, 0, 0. And then we need to fill in the location, the coordinates of O10. So if you see here, O0 and O10 at the same point, it's basically the global origin. And so that's going to be simply 0, 0. So 0, 0. And then this one appears here. Okay, and then maybe I should just write G10 and then we can move on. So G11 is, so it's the position of G1 in frame 1, which is this frame. Okay. So you can see that G1 is located along X1, right? We don't need to look at X0, only X1, because we need to find its location in frame 1. So you can see it's along the x-axis, and the distance from the origin, which is O10, is C1. So C1 along the x-axis, 0 on the y-axis, and then you need to put 1 just to make that multiplication work. Okay, so we can all put all this together. Let's compute the location of G1 in frame 0. Okay, let's call that, let's see, xg1, yg1 in frame 0 is, if you do the math, it comes out to be sine θ1 minus cosine θ1 minus cosine θ1 sine θ1 0, 0, 0, 0, 1. That's just writing H. And then G10, I just wrote down, it's C101. And so carrying out the multiplication, you should get C1 sine theta 1 minus C1 cosine here something. This should be actually, there will be a 1 coming up. It's a 3 by 1 vector, right? It's not 2 by 2, just because of the way homogeneous matrix is defined. So C1 cosine theta 1, and then there'll be a 1. So the last row just says 1 equals 1, which is true. So xg1 is C1 sine theta 1, and yg1 is minus C1 cosine theta 1. Now, that's not a big deal for a simple system like this, where you can just use trigonometry to figure it out. Just that if you look at more complicated systems, you see that this notation, this method of derivation can be generalized as in a numeric or symbolic package, as well as it just generalizes. So I recommend using that, even though you can figure that out just by using trigonometry. Okay, next we'll compute G2 in frame 0. It's going to be H20, G22. Yes, this formula is very similar to the previous one, where I just took the same form and replaced 1 with 2. Okay, H21 is H10, H21, and G22. So H10 is something which I already wrote down earlier. H21 is the rotation which relates frame 2 with frame 1. So if you look at this figure, it's what relates this frame with this frame. And you can see that they're related through this angle. So I just need to sub in for theta. I need to substitute theta 2 and use the same equation as here, but just put, instead of 270 plus theta 1, I just put theta 2. Sorry. Okay, so that's just the rotation matrix. I also need, this part is R21. Over here, I need to put what O21 is. So let's see what that is. Okay, O21 is, we just put that here. This is O2. So you can have two names. You can call it O21 or O20, depending on how you're relating it. So O21 is going to be the position of that point. Here it's also called P with respect to frame 1. Okay, so with respect to frame 1, which is this frame, the position of this point is going to be, it's at a distance of L along the x1 axis, along this axis. So that's what it's going to be. L0, 1. So let me just put a note here. It is position of point P in frame 1. Okay, and then G22. We can again quickly look at the figure. G22 is location of this point, G2, in frame 2, this frame. Okay, so you can see that the point 2, G2 is along the x2 axis, and so its location is simply C2 along the along the x2 axis. So it's going to have C2 for x, 0 for y, because there's no, it's not along the, it's 0 distance from the y2 axis, and then last one will be 1. So we have C2, 0, 1. Okay, so I'm not going to do the math here, but I just have the formula already done earlier. So it's x g2 in frame 0, y g2, x g2 in frame 0, y g2 in frame 0, and there'll be a 1 coming up equals something times, so this C2, 0, 1. This is something which you will get by taking this multiplication and putting it there. Okay, you don't have to do this because I'll show you that you can do it symbolically. You don't have to actually do any calculations. Okay, so what happens is when you do this calculation, the equation which comes out from this is L sine theta 1 plus C2 sine of theta 1 plus theta 2 minus L cosine theta 1 minus C2 cosine theta 1 plus theta 2, and then there'll be a 1. Okay, so the first row is xg2, the second row is yg2. Again, you can figure this out using trigonometry and check if the answers are right. Okay, so we got the positions, and those will be useful for the Lagrangian. We also need to get the velocities, because remember that the Lagrangian involves kinetic energy. So let's derive an expression for the velocities of g1 and g2. So to get the velocity of g1 in frame 0, all we need to do is we need to take the derivative of xg1 with respect to time in frame 0 and yg1 with respect to time in frame 0. Okay, so that's the expression. C1 sine theta 1 is for the x g1. So I need to take the derivative of that. So it will be C1 cosine theta 1 times the derivative of theta 1 with respect to time. And then same for the second row. So this will be C1 cosine theta 1 dot minus C1. Is it wrong? No, it's right. C1. So it's C. So minus C1. So derivative of cosine is minus sine. So it's will be positive C1 sine theta 1. C1 sine theta 1 dot. And then I just decided that I'm going to use a new notation for theta 1 dot. Normally people write it as omega. So I'll write this as C1 cosine theta 1 omega 1, C1 sine theta 1 omega 1. Okay, that's it. Now we need to also do this for BG2 with respect to frame 0. And that is taking the derivative of xg2 with respect to time in frame 0, y of g2 with respect to time in frame 0. And so let me just write down the formula. You can look at the expression I wrote down earlier and then take the derivative. So it comes out to be it's rather long. Need some more space. So it comes out omega 1 C2 cosine theta 1 plus theta 2 plus L cosine theta 1 plus omega 2 C2 cosine theta 1 plus theta 2, and then omega 2 C1 C2 sine theta 1 plus theta 2 plus L sine theta 1. I think this should be omega 1 plus omega 2 C2 sine. Okay, so I took the pains of deriving that, but you'll see that we'll get that from the symbolic toolbox. So it's a way you can confirm your answers. Okay, so we are done with the speeds. I should also point that omega 1 is theta 1 dot and omega 2 is the rate of change of theta 2. So that's what the omega 2 is in this expression. Okay, so next step is to compute the kinetic energy, which is T. Okay, remember it's half m1 Vg1 square plus Vg1 in frame 0 square. This is going to be, let me just write it this way. Okay, plus half m Vg2 in frame 0 square plus. Now, since there is inertia, I should also write the contribution due to rotational energy. So it will be half I1 theta 1, let me just write it omega 1 square. So that's the absolute velocity of link 1. And then for link 2, okay, the angular velocity of link 2 is, well, it's omega 2, but that is the angular speed of link 2 with respect to link 1. Let's go back. So we have theta 2, but that is the speed at which the link 2 moves relative to link 1, right? If you want to find the absolute speed of link 2, it would be theta 1 plus theta 2. So we always want to write the speed with respect to frame 0. So that will be the sum of the two, because the way the direction is, it's counterclockwise with respect to the y-axis. So it's going to be plus theta 1, with theta 1 plus theta 2, and not minus anything else. So plus of I2 omega 1 plus omega 2 square. Okay, so we're done with kinetic energy. Potential energy is going to be m1g yg1 with respect to frame 0 plus m2g yg2 with respect to frame 0. Okay, so that's the, I forgot to put the gravity in my figure, I think. So I forgot to do this. Okay, so gravity points in the y direction. So the contribution will only be to the y location of g1 and g2 along the y0 axis. So yg1 and yg0 have already been computed. So yg1 is right here, yg2 is right here. It's essentially this this row, second row. So I just substitute that inside this equation, and then my L is T minus V. So conceptually, it's very simple. You just do the subtraction. But if I tell you now, go ahead and substitute the value of a BG1, and maybe I should put it here because I think people won't know what this is. This is basically what you need to do is to compute that. You need to do xg1 square, so xg1 0 square plus x dot, sorry, y dot g1 0 square. So you need to take this component, sorry, not this one, here, square that term, and square this term, which is this, and then sum it. So that's probably very straightforward, right? No big deal. But now look at the other one. This term is going to be x dot g2 in frame 0 square plus y dot g2 in frame 0 square. So now you need to take this expression here, square that expression. So first row square it, second row square it, and then sum it up. So you can see the complexity of that calculation. It's pretty complex, right? And I think you spend so much time doing all the calculation, but the symbolic toolbox will do all that for you. And that's why we don't really do this by hand. Just come to this point where we set it up. Okay, so that's the second step. And the third step is to compute the equations of motion. Third step. So for that, we use the Euler Lagrange equations. So those are d dt of dl dq dot j minus d dq j equals qj, where qj in this case is going to be theta 1, theta 2, and then capital Qj will be all the external forces which are not do not have a potential. So if there's a spring that's associated with the potential, that will figure out in actually the V term. But if it is like a drag force or if it is a torque, then Qj will be the torque or the drag force and so on. So Qj here, in this case, we're looking at the pendulum with no torque. So it's going to be 0 for both the first and second. So since there are the Qj is theta 1, theta 2, you'll have two equations and they correspond to those 2 degrees of freedom. Okay, so well, when you do this calculation, you'll get a big giant equation, but it all will boil down to something like this. So when simplified, the equations will actually look pretty simple. It will have this form, and this is kind of universal for all systems which follow Newton's laws, F equals ma. They'll always come in this form. There'll be a 1 theta 1 double dot plus a 2 theta 2 double dot equals b1, a theta 1 double dot plus a 2 theta 2 double dot equals b2. So this will happen after simplification. Simplify. Okay, so A's are functions of theta 1 and theta 2. Okay, they'll only be functions of theta 1 and theta 2. And of course, the mass and so on, but system degrees of freedom will only be a function of the angles, would not be a function of velocity. It's kind of important later on when we do control. These, on the other hand, are functions of theta 1, theta 2, theta 1 dot, theta 2. So the velocities will appear in those equations. Okay, so once we have this form, what we need to do is we write this equation as a theta double dot equals b, where clearly A is a 2 by 2 matrix, and B is a 2 by 1 vector, and then theta double dot is theta 1 double dot, theta 2 double dot. So at each time step, what we need to do is we need to solve for theta double dot. It is going to be A inverse times B. Okay, so remember for projectile, we were interested in acceleration, x double dot and y double dot, right? Because those are the 2 degrees of freedom. In this case, we're interested in acceleration of the theta 1, theta 2, that's the theta double dot. And so you will get that, and that will, you need to integrate that once to get velocity, and the second time to get the position. Once you have the position, you can then plot them, or you can also animate, because you only need the position stamps at every time step, and then you can just do plot with the sufficient pause, and then it looks like a double pendulum. So what I'm going to do is I'm going to show you essentially how. Okay, I could have taken step 2. So step 2, everything is there in that this equations form. So I could just take that in symbolic toolbox and just get the answer. But what I did was, I'll just show you how to go from step 1 all the way to step 4 in Python. So all these equations are derived in Python, and you get the answer versus trying to do this. So in case I did some calculation mistakes here, for example, then they will not matter because my code hopefully is right and it will give me the right equation. Okay, so this is how it works. I essentially derived these equations and took the pains of deriving them once. And then if you want to derive from another system, I don't start from scratch. I just take this code and then just start editing it the right place. And and I highly recommend you do that. Don't try to, it's not like solving a problem where you were taught to solve problem by yourself 5 times or 6 times, I don't know. Don't do that for coding. Just copy this and just edit it. So it's important that you understand this code, and then you can modify it to suit your own purpose. I recommend doing that for almost everything you will do with respect to coding. Don't write your own code. It's just not worth it. Let me run this code first. Okay, so I've used a slight different notation, and I should have pointed it out. You see here there's M's and C's and G's. M is same as A, and C plus G is actually B. So let me note, make a note of it here, because I think you'll surely forget. So A equals M and B equals C plus G. Okay. I wrote C plus G because it turns out that the B term, the right-hand side, is split into 2 parts. One due to gravity, that comes in G, and one due to what they call Coriolis force, which involves accelerations, and so that will come in C. And so it's, some people prefer writing it that way. Some people just keep it as B. Okay, but it's not important here. In this course, it's enough to have them as B. If you're doing some control, then you might want to differentiate between them. So first step is define all the symbolic quantities. You need to tell Python that these quantities are, you need to keep them as whatever they are, and your answers should be in terms of those. So all those are defined. Now I try to write sort of comment this code so that it corresponds to what I did there. So first step is position vectors. So you can see I did it 270 plus theta, and then I got H01, H12 from my notes, C1, G1, C2, G2. The C1 is actually 010, and I think you can relate it once you see my notes. It's basically 010, 020, 021, and so on. XD1, YG1, XD2, YG2. That's the position. So this basically gives me the positions. Now, once I have that, I can compute the velocities. I've used something called a Jacobian. We'll teach out what Jacobian. So next, after we finish this, we'll actually get to Jacobian. So Jacobian is an easier way of computing the equations. But what you can do is you can also do you can also differentiate. You remember I talked about diff earlier in my sometime back. I talked about diff. You can use diff also, but Jacobian is a nice cleaner way of doing it. But don't worry too much about that, because after this we'll talk about Jacobians. Okay, so that gives me VG1, VG2, and that will have 2 components, X component, Y component. Then I get the Lagrangian, which is this whole term T, V, which is straight from the notes, L equals T minus V. Third step is derive equations. I need to define what that theta double dot would be. It's defined as Q dd dot. Put it here as, this should be theta d dot. Okay, and now I took a lot of pains in writing this equation so that you get the answer by writing very little code. And so if you look at it, if I look at this of somebody's work, I'll find it really hard to understand this. The way I worked it out is first I try to write these equations line by line. I just took those equations, I wrote them down. Then I tried to see if there was a pattern in those equations, and based on that pattern, I rearranged that so that it is very compact. Now, I recommend that it is written in such a way that even if you have 10 equations, it will actually do the work for you. So you don't have to really go and try to debug and understand this. I would just recommend that you just, if you're writing equations, just copy paste it, it will work. The moment you give it the right dimensions for q d dot, and you define L and some other things like q dot is theta 1 dot, theta 2 dot, it'll actually do its job. Other way to do it is to do hard work, is to write this equation. So it's up to you. So then I do this thing where I try to get the equations of motion. And this command subs is you substitute the values. And so the way this is done, and this is actually a trick, it's nothing to do with robotics. If you have a theta 1 dot plus, sorry, a11, a12 theta equals v1, sorry, equals minus v1 equals 0, right? So your equations of motion. So this EOM gives you two equations, EM0, EOM1. Let's say that the first one is EOM0. Now, I wrote down it is that form, but when you look at it, it'll be like, if you just print it, just to give you a sense of what it looks like, print EOM0. Okay. If you, I don't want it to go all that. So one way of debugging this, I like to debug it this way. Just write something which will cause the program to give you to stop there, right? So it will only print that and won't go forward and save you some time. So Control Shift B. Okay, that the error is not important, but what we wanted was above that. That's basically this. Okay, now I could have maybe simplified a little bit by putting simplify. I think that's a short. Let's take too much time. Let's see if I can. Okay, so it's not too bad actually. It's just one page long. So if you do it for more links, then you see it's much bigger. Anyway, so this is the equations. Now, what I'm saying is from this equation, how the hell will you figure out what A11 is and A12 is? And so the trick is this, that I know that the form of the equation is this. Right? Always A11 appears with theta 1 dot and A12 appears with theta 2 dot and so on. So what I do is, in order to compute A11, all I do is I can put theta 1 dot equals 0. Sorry, to compute B1, I put theta 1 dot double dot 0 and theta 2 double dot equals 0, and that will give me B1. So I substitute those values, I get B1. Then if I want to compute A11, what I do is I put theta 2 d dot equals 0. I know B1, so I'll subtract the B1 from this term, or add B1 to this term, and I'll put theta 1 dot equals 1, and I'll get A11. And so you can actually compute A11, A12, and so on by that way. That's one trick. The other trick is to use Jacobian. So Jacobian actually will give you that. And again, I'll talk about Jacobian next class. Here I've used this trick to compute this B1. B1, I told you, has a gravity term and a non-gravity term. So basically, it turns out the gravity term has only N1, N2. Yeah, so this is the gravity term. So the gravity term does not have in it angular speed. And so if I put angular speed equal to 0, then whatever remains is the gravity term, and that's how I got the gravity term. And once I know the gravity term, I can subtract it from the non-gravity, the total B1, which is N1, and get C1. So they're just tricks to get the answer, but they're not very essential. So this is actually also N. Okay, and so what I did was I wrote down A, C, and G, and then that's the output. Now, once you have that, we can do a simulation of this, and I'll show you what I do with these equations. So once I have those equations, which are, on this, hope I removed that comment. Okay, so this is just, sorry, the simulation. Later on, then I'll show you where I actually copied down the code. That's a double pendulum, and it's basically has C1 equals C2 equals half of length, so it's right in the middle. And I think I simulated for a few seconds. This is the plots of angle and angular rate versus time. As I said, this derivation gave me M1, M12, and so on. All I did was I took it and I pasted it in the right-hand side. This code is pretty long too. Okay, so I pretty much copy pasted that code right here. M1, C1, G. I got A, which is said distant. B is C1 plus G1. It's actually negative of that. And then I do A inverse times B, and that gives me theta dot, theta1 double dot, theta double dot. And then I need to pack that as the state. So velocity, angular acceleration, angular velocity, angular acceleration for two links. And that's what is returned. So this is my right-hand side. And that's called, it's right here. I used ODE to integrate them. I need to define some initial state. So right now the pendulum, if you remember, downwards is 0. So if I do 180, which is pi, it's vertically up, but I shift it by a little bit, 0.01. And then I impart a little bit velocity to it, to the link one. The other link is at 0. Pass the parameters, and this is the right-hand side. So that's one part of the code. And then you do animation, which basically gave you that plot. So running this, so we can check this quickly. We can just put that and then put 0. And then it probably will stay there. Now, in a perfect world, it will not stay like that. But in simulation world, it can stay like that because there's no disturbance. Right? It fell there. So there's probably the integration error crept in and it just